Let's get us started. We were talking about discriminant analysis. Now we've already covered quite a bit of ground in these first several lectures of the course. Please do review all this. There's a new homework that's been posted, and there's going to be a new project coming up in the next day or so. We need to review all this to be extremely familiar with all this methodology, these methods, because everything else that we're going to do in the second part of the course is going to depend on our understanding of these concepts, right? You cannot work on modern machine learning algorithms, pattern recognition algorithms, if you don't know how to develop these methods or why you develop these methods in specific ways. If you are to develop top-of-the-line machine learning algorithms down the line, then you have to learn to interpret these different steps that these algorithms have. And we can only talk about those if we understand the terminology and we speak the same language. Okay, so let's go back, maybe we can go back very quickly to what we had. Remember that we had this equation that we want to build a classifier that's base optimal under certain conditions. And our classifier is the argument that minimizes this di of x. And this is nothing else than the discriminant function, right? So we call this a discriminant function. And we want to find the I, meaning the class I. I will go from 0 to C minus 1 or 1 to C. C, the number of classes. And for normal distributions, we showed that the classifier, the base classifier, is given by x minus mu I transpose sigma I inverse x minus mu I plus the log of sigma I minus 2 times the log of the priors. Okay, so that's the classifier that we've derived. Obviously, this classifier is nonlinear with regard to x because I have a square value here. But in the homoscedastic case, in the case that sigma I is equal to sigma for every class, for every covariance matrix that I have, then this equation simplifies, right, to a simple linear equation. And that's what we want to take advantage of. Now remember that this equation that this simplifies to in the homoscedastic case meaning this, then we have that this classifier, right, this, let's call it V or W, we've called it before, has to be proportional to sigma inverse times mu1 minus mu2, right? Okay, and the reason for that is the reasons for that are very simple. If I have in my feature space, I have 2 Gaussians, and these Gaussians have this different mean but the same covariance matrix, and this covariance matrix has been whitened. So this covariance matrix is the identity matrix. It's the identity matrix mu2, mu1. Then obviously the optimal classifier that I can obtain from here is given by the vector that defines the basis vector, I should say, that defines the vector mu1 minus mu2, right? Because mu1 minus mu2 defines this space, right? And once I project my covariance matrices onto that new space, then this area right here gets projected into the same area, right? So I'm going to have now, in this one-dimensional space, I'm going to have this. And this area right here corresponds to exactly this area right here, meaning that the empirical error that I can compute in this space of p dimensions is the exact same empirical error that I'm going to compute in this space of one dimension, right? So I can go from Rp to R1, right? So I can reduce the dimensionality of my space by p minus 1 and still not lose anything for classification purposes. Okay. Now, the way we're going to compute this vector is the eigenvector of a couple of matrices, meaning that it's going to be, it has to be, rather, this equation right here, right? So I'm going to say sigma inverse times mu1 minus mu2 divided by, because this basis vector or eigenvector is going to be, has to have norm 1, I have to normalize by this vector right here, right? Okay. So the norm of this, right? And remember that this is, of course, the whitening function right here. This is that vector. That is the base optimal. This just simplifies this or converts this vector mu1, mu2 vector in the whitened space into a basis vector. Now, this is it, and this is the famous theorem that I gave you last time, that for two normal distributions, right, that define the underlying distributions of two classes, each class drawn, or it's the samples of each class drawn from these two normal distributions. The first normal distribution is given by mu1, the second one by mu2, and both distributions have the same covariance matrix sigma. Then this leads to the base optimal solution, meaning that the empirical error in the original space and the space defined by V are exactly the same. Okay? But there are several issues with this approach that we derived last time, and let's go through them. Okay? First one is that thus far we have only defined this for two classes, right? This is a fantastic theorem. It says if we can go from p dimensions, whatever the p is, could be 100 trillion. We still can reduce this to 1 and not lose anything, only if we have two classes. But what happens if we have more than two classes? So what happens if C, the number of classes, is larger than 2? Then in that case, what we can do is we can extend this vector right here into a scatter matrix, into a metric, right? A square and a positive semi-definite matrix that defines a metric, as we've seen before. That includes all the possible pairs. This is called the between class scatter matrix, SB, and it's given by the sum, let's see, from 1 to c minus 1, and then j from I plus 1 to c. Okay, so I'm going to go first class 1, and then for class 1, I'm going to consider 2, 3, 4, 5, 6, up to c, right? For class 2, then I'm going to consider 3, 4, 5, 6, 7. I'm not going to consider 1 again because I've already done this. 1, 2, 2, 1, same thing, right? And then I'm just going to have this mu I minus mu j, mu I minus mu j transpose. And I'm going to add here in these equations, which I didn't have here, but I could have added them, right? I could have added them here as well. I'm going to add the priors, pi and pj, right? All right. Now, unfortunately, I'm not sure. So now what I can do, let me do that. So now what I can do is redefine this equation that I have here, right? By substituting this thing here that I have, right? So my vector v now has to be proportional to sigma inverse times SB, right? Which measures the same thing, right? But now this is no longer V, rather this is capital V, which is several eigenvectors, right? Why is that? Because in this equation right here, this is of P by P dimensions, correct? So this is at most rank P, right? If it's full rank. Could be smaller, typically will be smaller, but at most it's rank P. What's the rank of this? It's just a vector, so it's rank 1. So if I have a product of 2 tensors and one is smaller rank, then the smallest rank wins, right? So this product is for rank 1, meaning I only have one vector as a solution, right? This one. But here, I have the product of these 2 matrices, right? This is at most rank P, but what's the rank of this? That's what we don't know yet. We would like to know what the rank of this is. Now, we have this equation, and in your homework, I ask you to prove that this equation can be rewritten. It's just a few steps as follows. The sum of I from 1 to c of pi, remember pi, it's a prior, mu I minus mu hat or bar, mu I minus mu bar. We'll remember mu bar, it's the sample mean, right? So it would be 1 over n, the sum of all the mu i's, right? From 1 to, I'm sorry, not n, c. Okay? So in your homework, you need to prove this step, couple of derivations. And now, if we have it in that form, anyone can tell me what is the rank of SB? It has to be smaller or equal than, what is it? C. That's almost correct because you have C such vectors. They define a C minus 1, right? Because remember, if I have 2 vectors, they define a line. If I have 3, they define a plane, right? Obviously. So C minus 1. But very good. Excellent. So this is at most C minus 1. This is at most P. Generally, P is much larger than C minus 1. But at any rate, the rank of sigma 1 inverse SB is smaller or equal than the minimum of the rank let's say, when we say P and C minus 1, right? OK. So in general, we have this, correct? Now, in general, P is larger. Not always, but in general, P is going to be larger. So this is smaller or equal than C minus 1. OK? Now, with this, I can now derive the same equation I derived before. Now I have capital V transpose SB V divided by V transpose sigma V, right? This equation is exactly the same as this one that I have right here, okay? But now with SB instead, right? And of course, I want to find the V's that maximize this, right? And we know how to solve this. This is SB V equals sigma V lambda, capital lambda, right? And this is our famous generalized eigenvalue decomposition equation. You can move sigma to the other side if you prefer, as we had here, right? And say that sigma inverse SB V equals V lambda, right? And now the columns of capital V are the subspace that gives us the base optimal discrimination of these C normal distributions. Okay? Still base optimal. So this is still base optimal under the homoscedasticity assumption with normal distributions. This is still base optimal because we haven't changed anything. Meaning that the empirical error that I can compute in the original space of P dimensions or in the space of C minus 1 dimensions is exactly the same, right? But something has happened, hasn't it? While doing these derivations. What has happened? Something we may not really be very happy with. What just happened? So now I can change the theorem that I had before, right? I can say for any space of P dimensions in our P or CP, right, the complexum of P dimensions, I can map everything onto a subspace of C minus 1 dimensions, where the empirical error of the in the original space of P dimensions is exactly the same as the empirical error in the space of C minus 1 dimensions, right? But that's not as strong as this theorem, right? Because this theorem said what? That it can map from P2 onto 1 dimension, right? What just happened? This is C minus 1. And the reason is that this is true. It's base optimal in C minus 1, but it's not base optimal in the one-dimensional space anymore. If I only compute the first eigenvector, that's not base optimal. Okay? It's only base optimal in the C minus 1. But the reason it's base optimal in C minus 1 and I need C minus 1 is because I used a trick that you're all very familiar with, hopefully by now, that it's called, anyone can tell me which method I have used to do these derivations? Don't say that that shyly. Just speak up. I heard it, but I don't know who said that. What did we use to extend this? How about if you just say the first method that comes to mind? What's that? Linear least squares. Yes, right? I mean, does this look familiar? This is the linear least square solution, isn't it? So this is indeed, all I did is I used linear least squares, right? So I said, well, this is my solution for the one-dimensional space. But I have C classes. So what I'm going to do, I'm going to write down all the equations. That's all I'm doing here, right? Write down all the C minus 1 by C over 2 equations, right? This is the same as, so if I have C classes, I can go 1 to 2, 1 to 3, 1 to 4, 1, right? So for every C of the C classes I have C minus 1 matching pairs, right? But because 1 and 2 and 2 and 1 are the same, I can divide by 2. So that's my number of equations that I can create. That's exactly what I did here, right? I just lay down all my equations, like in linear, not like in linear least squares. This is linear least squares, right? You lay out all your equations. And once you have all your equations, then you solve it using the classical eigenvalue decomposition, which we showed. It's the least square solution. So that's why this is still base optimal in the C minus 1 space, but it's not it's not base optimal in the one-dimensional space. In the one-dimensional space, this is the least square solution. Okay. All right. So we certainly are going to. We will revisit this today because we certainly want to improve that if we can. Okay. But before I improve on this, let's go back to this and now also this, right? So I have two main results. One of them was this one. This is for C equal to 1. I'm sorry, not 1 makes no sense. 2. And this one here is C larger than 2. Okay. There's another problem that we have with these two solutions that we have derived thus far, right? One was for this one, only 2 classes. We've solved this. Now, what is the other problem that we have? That we are assuming sigma is constant, so the classes have to be normal homoscedastic distributions, right? Well, generally, that's not going to be the case. It's absurd. It's rare the case when the classes are defined by normal distributions, let alone homoscedastic normal distribution. So, so how can we extend these derivations that we have here in the case that sigma is not constant? Well, we can use another trick, right, that we are very familiar with right now, or by now, which is we can just compute the simple mean, right? Remember the simple mean? I said super useful for everything. I could compute the simple mean. So in the heteroscedastic case, we're going to have sigma I, right? Generally, they're going to be different. Sigma I and sigma j are going to be different for I different than j, but they don't have to be. But I'm going to have sigma I defining the covariance matrix of the ith class. And what I can do now, I could compute the simple mean of these different distributions. So I could do sigma I and then sum over from 1 to C, right? 1 over C. And that would give me the mean, right, of my sigmas. Another way to say this is using what's called the within class scatter matrix, but it's the same thing. Both things are exactly one and the same. Which is SW, which we can write as let's see. I'm going to sum from 1 to C. That's for the number of classes. And for each class, let's say I have n sub I samples. So I'm going to sum over from 1 to ni. And then remember that the covariance matrix sigma I is nothing else than xij, where xij is the jth sample of the ith class, right? Minus mu j, xij minus mu j transpose. And then I multiply this by the prior, right? And I probably normalize it by the number of samples if they are not equal. Although ni, it's probably going to be included in the prior, but it may not be. So depending on your formulation, be careful. You may not need ni if the prior actually specifies the ratio of samples that you have. But if it doesn't, right, if pi specifies something else, where's the probability of observing the particular class, then that will be necessary, right? OK. So obviously, this is the same as this. It's just a different way of writing it down. And then that leads us to our third solution, which is the same one as this one. But now, because the covariances are not the same, I can use SW or sigma bar, again, same thing, and get this third solution. OK, so I have, this is my third solution. This was my second solution right here. This was my first solution. OK, I have 3 solutions. This is for homoscedastic Gaussians, just 2 homoscedastic Gaussians. This is for homoscedastic Gaussians, but any number of them. And this is for any number of heteroscedastic Gaussians. OK? Make sense? Now, if I were to use this, right, or this I can still use in the heteroscedastic case. But then in that case, sigma is changed into sigma x. OK. Now, sigma x, remember, is the covariance matrix of all the data, right? Of all the samples belonging to all classes, right? And these 2 equations that I have there will give you the same C-1 dimensional subspace. Now, if you use less than C-1 dimensions, they will not give you generally the same subspace, right? So the order of the eigenvectors that you get with these 2 versions of 3 is different, but the end result, the base optimal subspace of C-1 dimensions, are identical, right? And that is because sigma x and, sigma x, SB in both equations are identical and define, therefore, the same subspace, right? There's just nothing else you can do. This is the subspace defined by SB. OK. And SW and sigma x, it's just a way of whitening your space, if you will. So it's nothing else than a scalar and multiplier. And that's what scalar that changes the eigenvalues but cannot change the eigenvectors, right? So the eigenvector is going to be the same. It's just going to be ordered differently. We can use all this to define one of the simplest but still very powerful classifiers that we will see in this course, which is called the nearest min. This is a very simple classifier. It's actually used quite a bit within some other spaces or some other subspaces or methods. But you can apply it on its own. And it's just basically based on the derivations of discriminant analysis. By the way, this discriminant analysis that we have derived, 1, 2, and 3, all three versions, are called linear discriminant analysis. Or LDA for short, right? And it's called linear because it's based under the assumption of homoscedasticity, homoscedastic Gaussians, and under that assumption, the base optimal solution is a hyperplane, right? So linear equation. That's what that linear means. Some people call it Fisher discriminant analysis because that basic idea was originated by Roland Fisher, the famous statistician, the father of modern statistics. All right, so using this, we can derive this nearest mean classifier. So let's see. Let Ti, or just T, what with Ti? Hold on. Let's just do T. I think that's wrong. Be a test vector or feature vector to be more accurate. Okay. So I have my sample vectors, xi's, and my test vector that I don't know to which class it belongs to, T. Now, our equation hasn't changed. It's the first one I draw on the other side of the board. I want to find the argument that minimizes this distance or a discriminant score, the I of T now, right? Okay, that's fine. I1 through C, right? I can only take a value between 1 and C. Okay. Now, for the nearest mean classifier, I can have di of T be equal to, I'm going to give you three options, okay? Number one, T minus mu I transpose T minus mu I. Second option is going to be T minus mu I transpose sigma I inverse T minus mu I. And the third option is T minus mu I transpose sigma I inverse T minus mu I plus the log of the determinant of sigma I plus 2 times the log of the prior. Okay? Now, these three correspond to 3 different cases that we have considered here. Okay? So let's start with the last one. The last one, this equation right here, is nothing else than the same equation that I have in here, right? The exact same equation. So that is just the base classifier for normal distributions, right? So what does this do? It finds the class with highest probability, or since this is written as a distance, you can consider it as the distance from your feature vector to the mean or the center of the distribution of each class, right? And that's why this is called nearest mean, because it finds the mean that is closest to it. Now, remember, if I had the Euclidean space, right, if sigma was the identity matrix in this last equation, then I would be in the Euclidean space, flat, right? But because sigma is not the Euclidean this is not the identity matrix, that means that the space is vent, right? So maybe I have a point here and a point here, right, on each side of that curve, but they're very close to each other, right? Extremely close, even though in the Euclidean space they would be really far apart, right? So depending on the space matter, that's what this means. The priors matter, everything matters. Okay. So that is the most generic base optimal solution for normal distributions. The second one, right? So I talked about this already. Now let's go to the one in the middle, this one, the second one. This is still base optimal under one particular condition, which is for, anyone? For equal priors, right? So if my priors are identical, then that's still base optimal. And this one is still base optimal if I have equal priors and something else. And the covariance matrices are the same. So you're homoscedastic. Yes, you had a question.
For the second one, if this is base optimal, should we add one term y, the determinant of sigma I?
Oh, yeah. Yes, you're correct. Yes, thank you. Yeah. All right. Very simple classifier to implement in MATLAB. I mean, this is like 3 lines of code, literally. You can probably do it in one, but say 3 or 4 lines of code. Or in Python as well. Extremely easy. This should be something that you implement tonight. And you just put it in a folder. And every time that you do anything in machine learning, you build any classifier in machine learning, you compare it to this one. I mean, it takes just a few seconds. Right? It's fantastic. Now, there is a potential problem with this when you apply it to real problems, right? To a problem like the ones that you had in Project 1. Anyone can tell me what the issue may be in the computations that you need to execute to get the nearest mean? There is a computation there that may actually be hard. The inverse of what? Right, but what's the problem with this covariance matrix? There are 2 issues with this covariance matrix. Right, so one thing is that it may be rank deficient, right? So it may not actually have an inverse. That has an easy solution. You can do sigma, and there's something that we'll see later on in the course. It's called to add a regularizer, but we'll get to that. Don't write this down. So you can add to sigma I, you can do sigma I plus lambda or alpha, the identity matrix for alpha really small, right? And then you just basically make it full rank. But there's another problem, even under this condition. What's the problem? That sigma can be what? Huge, right? Yeah, very good. Sigma can be huge. You know, imagine that you take pictures of objects as some of your data in Project 1, right? The images you have. And I take pictures with a camera. It's a 10 million pixel camera. This is 10 million by 10 million. Right? So these computations grow really fast. These matrices grow really fast, and the computations become really intractable. Not only is it rank deficient unless I have 10 million independent or non-linearly dependent samples, right? But it would be extremely computationally expensive. But we already know of an approach, of an algorithm that we can use to solve this. What is this called? Starts with a P. PCA, right? So what you can do is you can project this onto the first QPCs that keep a percentage of the variance, right? 90, 95, 99% of the variance. The covariance matrix, you, of course, will need to also project the means, right? And everything else, obviously, the vector that you're trying to compute. But basically, what you're doing is, if I'm in high-dimensional space, right, I'm going to first compute the PCA space, as we have done before, right here. I'm going to project my data points and my covariance, right? So if I have a 3-dimensional distribution, now I'm going to end up with a 2-dimensional distribution in this simplified case, and then I'm going to work in this PCA space, right? That simplifies things dramatically. You already know, because of your project, how to even compute PCs when the number of samples and the number of dimensions are tremendously large, right? And obviously, one simple solution, there are many solutions to this, but one simple solution is you compute the PCs of a subset of samples at a time until you cover all the samples, right? And that will give you several PCA spaces. And then you have to compute the common PCA space. And do we know of a technique that finds the commonality, the correlations between all these dimensions? I think it's called PCA. So you apply PCA on PCA, right? And you get this space. So it's actually really simple to do computationally to get these PCA spaces. And that will allow you to run these algorithms super fast. Now we're talking about maybe 6, 7 lines of code instead of 3, right? But it's still super simplistic, right? So a great algorithm to implement tonight. Have it always ready, because this is something extremely useful. All right. Let's see. So let me go back maybe here, okay? This equation here, or here, same thing, right? Remember, that comes from here. This is an extension where we have changed, right? We have changed this term right here, right? So now I have, let's see, I have, this one is optimizing. It's trying to find the max, right? The basis vectors V whose columns are the basis vectors that maximize V transpose. Now I have SB, same as here, SB, and V transpose SW, or sigma X, right? You can write this down as, to do this, as maximizing the trace. You could maximize the determinant of both. It doesn't matter. They all lead to the same solution. Okay? The trace is the one that we've derived earlier. Remember? When we talk about PCA, that's the one we've derived. Now, obviously, that's the same as PCA, because I have SW inverse SB. This is symmetric, positive, semi-definite. This is also symmetric, positive, definite, right? And therefore, this product is symmetric, positive, semi-definite, right? There are no tricks. But what do we know about a symmetric, positive, semi-definite matrix? Excuse me. What do we know about it? What does it define? Right? Remember here. What is this? What's this term here? Okay, and it's a symmetric, positive, semi-definite matrix, right? And what does it define in this equation right here? What's this? What's this called? We saw this before. This is the distance between two vectors, x and mu I in that case, right? Okay? And this is the metric that I use in that space, right? So in general, any symmetric, remember, positive definite matrix in a vector space like this defines a metric, right? And this quadratic metric gives me a Hilbert space, right? So this is what defines a Hilbert space or vector space. But this is the same thing. You see? This thing that we have here, right, or here, which is the same, this is yet another symmetric positive semi-definite matrix. And therefore, this defines a metric. So all we have done is we've changed, right? When we were working with PCA, we were using sigma x or sigma I for each class. And now we are using a different metric. So in fact, all we are doing, and remember that ICA, when we derived the Fourier PCA to extract the independent components, remember that? That was actually the same thing, right? All we are doing every time is finding a different metric, which means that, again, we start in our feature space, which is defined by this basis vector and that basis vector, right? And then we deform this space somehow with our metric. And now the distances have a meaning, right, to us, because these two vectors right here may correspond to the same class, this vector and that vector, right? And if I change the metric in a way, they are in the exact same position, right? And a vector right here in the middle that corresponds to another class is still far from these two, right? So that's exactly what we want. We want to define metrics that, in the case of classification, that pull samples of different classes apart and bring samples of the same class close together, right? And that's exactly what SB and SW are doing. Look at this. SB measures, let's see where we've defined SB, right here. You see SB? SB measures the distance between each sample mean and the global mean, right? Or said in another way, because these two equations are exactly the same, the distance between each pair of sample means, right? And what do I want? I want to maximize this, right? Obviously, I want to maximize this metric. That's why this is in the numerator, right? Here, because I want to maximize it, right? I want to maximize this equation. But what is SW measuring? SW here measures the distance of samples xij that belong to the same class j, right? So these are, say, images of houses or images of cars. But all the images that I have here, xij's, are of the same category, either houses or either cars, right? Or if you are in the speech recognition, it would be all the words said by any person in the world that correspond to the word, or all the sounds, excuse me, spoken by any person in the world that correspond to the word house, right? Or to the word car, so on, right? And it's all the same thing. But so what are we computing? We're computing the distance of every sample in class J to its mean, to its sample mean, right? And what do we want? We want this distance to be small. We don't want the samples of class cars to be away from the mean of cars. We want it to be as close to the mean as possible, right? Ideally, if they are all the mean, then all the cars would be represented by a single point in my feature space. That would be ideal. But at least I want them to be as close to each other as possible. So I want to minimize this metric. That's why I inversed this, and it ended up in the denominator, right? Because I want to minimize this. So maximizing this means I'm minimizing this, right? which means that I can change these metrics at will. I can change these metrics to represent anything that is useful to me, right, in my problem. Now, for homoscedastic Gaussian distributions, I already have the solution, the base optimal solution for the two-class problem. And I have the C-1 dimensional subspace base optimal solution for the C-class problem. But how about for the heteroscedastic distributions? I don't, right? But I can now change these metrics for some other metrics. So let's see how we can do that. OK, so what I'm going to do, I'm going to define a new metric. So for simplicity, let's assume that the data has been whitened. So I'm going to assume SW equal to the identity matrix, or you could assume that I have whitened the whole data. Doesn't matter, either way. OK. So I have the trace, right, from over there of, is it mu1 minus mu2 times mu1 minus mu2. This is for two classes. We can generalize it easily to more classes in a second. Maybe we want to add the priors or not. If you want to add them P1, P2, V transpose V, and then here V transpose V. Okay. Now, if I compute the eigenvector associated to non-zero eigenvalue of this equation, now V, remember, we know what V is going to be. It's going to be proportional, right, to mu1 minus mu2. And the corresponding eigenvalue is going to be, let's see, it's going to be the trace of mu1 minus mu2 times mu1 minus mu2 transpose, which is nothing else, right? The trace of this matrix, which is nothing else. Oops, I forgot the transpose here. Okay. Which is nothing else than the 2 norm of mu1 minus mu2, okay, squared. That's what this is. Remember the trace, right? Which is the sum of the diagonal elements. And that obviously is the Euclidean distance that we have defined before. OK, so this is the solution for oh, I erased it. The solution that was here, right, which is for the two-class problem, right, our first solution. Oh, yeah. And that solution for the two-class problem is given by the 2 norm, right, or the Euclidean distance. What happens if I change that distance for something else? Remember that I introduced when talking about base, bounds, upper bounds for the base error, that we used something called the Chernoff bound, or we derived the Chernoff bound. And the Chernoff bound gave us the Chernoff distance. Why don't we use that? Let's try to use a Chernoff distance. So now the Chernoff distance in general is given by, let's see, negative, I think, the log of d1 alpha x d2 1 minus alpha x dx. Okay. This is a general definition. Now, for our particular case, so we want to minimize this in the general case. Now, for our particular case with normal distributions, we showed that this is equal to, let's see, mu1 minus mu2 transpose alpha sigma 1 plus 1 minus alpha sigma 2 inverse, right? So now this is exactly the same. This is what we derived when we were talking about the bound, right? This is exactly the same as the one I would have here, right, for a symmetric matrix, but now it's multiplied by alpha and 1 minus alpha, right? Remember from the Chernoff bound that this is the parameter that we're using. And then, of course, mu1 minus mu2. This is our distance. And then we need to add the log of the determinants of the two matrices now, which is exactly the same as this. So I have alpha sigma 1 plus 1 minus alpha sigma 2, right? Whoops, my bad. Sigma 2 and sigma 1 to the power of alpha and sigma 2 to the power of 1 minus alpha. Okay. Okay, so this is the same that I had before for the bound, right, with normal distributions. So what we want to know here is how can we obtain this result, right? Because for when we have this case, right? When we had this case here, we obtain this result. When we obtain this result instead, what would be the equivalent equation here, right? What equation is going to lead us to this eigenvalue, right? And this is actually very easy to show that there's a very simple solution. And the solution is C for Chernoff now, similar to the between and within. Now we use the Chernoff here. It's equal to S inverse 1/2 mu1 minus mu2 mu1 minus mu2 transpose S 1/2 inverse plus 1 minus alpha of the log of S minus the log of sigma 1 minus 1 minus alpha the log of sigma 2. Okay. And I need to multiply this by 1 over 1 minus alpha, where S, it's given by sigma 1 times alpha plus 1 minus alpha sigma 2. So let's look at this for a second. Now, this was given by the trace of this equation right here, right? This one. This is what this gives us the Euclidean distance because there's an identity matrix here. And in that case, if I use this, I'm going to get the exact same thing here, right? The distance of these two vectors, but now I need to multiply this by this factor that I have here. You see that? Right? The trace of that is going to be given by this new metric, right? It's the same thing. Okay? And then this other term comes from this. It's not as important. Okay? But the thing is, you can derive new metrics like this one, right? That actually can substitute SB in that case, or you could derive also other solutions for SW, right? So in this method, this is called heteroscedastic discriminant analysis. And you still have to define what alpha is, right? And alpha is defined generally as P1 and 1 minus alpha as P2 to represent the priors such that these priors right here, right? Such that in this case, for homoscedastic distributions, this still leads to the base optimal solution. Okay? So we can easily now show as an optional thing to do for you tonight is just to show that this is exactly the same solution that the one that we had before, right? Now, to extend this to more than two classes, you use the least squares approach that I have used before, right? And you combine mu I and mu j into different equations and apply the same thing. Okay? The thing again is you can change the metrics SB and SW by anything else that that you determine appropriate for your problem. All right, maybe see if we can show very quickly a couple examples of all this. Is it coming up or not? Yep, there we go. All right, so remember PCA, right? PCA computes the correlations between the features in our feature space. So if I have this first feature and that other feature, in that case, these two features are 100% correlated, right? And the first basis vector of the convergence matrix defines this correlation, right? In this case, they're not perfectly correlated, but there's still a correlation, and PCA will find us, right? Now, in one of your homeworks, you have implemented eigenfaces, right? You have used faces to find the PCA space of or the PCA space that defines the images of faces in the image space of all possible images, right? So if I take images with a camera that has p pixels, then R, the domain, the real domain, RP defines all the possible images I can ever take with that camera, right? All the possible images. And there's a subspace, right, the PCA space of all images of faces that has to be of a smaller dimensionality than P, right? It cannot be the whole space because whole space can represent every image you have ever seen. Now, when you compute the PCA of the covariance matrix of all the samples of faces, right? How do you do that? You take the image, you vectorize it, right? And then you compute the covariance matrix, you compute the sample mean, you compute the sample covariance matrix, and then you compute the eigenvectors of that covariance matrix. And those eigenvectors that you obtain are called eigenfaces now. Now, these eigenvectors are the basis vectors that define the subspace. But you can reshape these eigenvectors, right, which are of P elements. You can reshape them back into an image, right? So if you reshape them back into the image, so you go the inverse of what you did. Before you did from image to vector, now you go from vector to image, right? This is what you're going to see, right? You're going to see this so-called eigenfaces. And what this defines, the brighter the color here, right, the most relevant that is, the more correlation basically there is between these pixels, right? And the darker the color, the less there is, right? So you can see that in the first eigenvector, everything matters basically in the face, right? Everything is sort of correlated with something else. What a big surprise, right? But as you go in deeper and deeper into the eigenfaces, you see patterns that start popping out. So for example, here you see lots of correlations. You see this white circle right here. Anyone can tell me what this is? Eyeglasses, right? It's actually finding out that when you have eyeglasses, there is a strong correlation in those pixels. Well, yeah, not a surprise. There's a strong correlation above the eyebrow, right, under the eyebrow. There's strong correlation here around the mouth. There's a strong correlation here within the mouth, within the eyelids, right, and so on. Again, more eyebrows. They get noisier and noisier as you get deeper and deeper into the eigenvectors. And that's something related to what we talk about, the variance, remember? That variance, that eigenvalue associated to these eigenvectors come smaller and smaller and smaller, and they're just basically representing noise at one point, right? But as you get closer and closer to the noise, you get noise merge into this real data. Now, if you use more faces to compute the PCA space, then obviously their eigenvectors look smoother because then the noise gets eliminated in the computations. Now, note also that because I now have the PCA space of faces, right, I can generate new samples of faces that I have never seen. I can draw a vector on that subspace, right, that hyperplane that defines my subspace, right, PCA space. I can draw a vector from it, right, randomly, and then convert it back into the original image space, right, of RP, and then visualize the image. And what do I get? I get a new instance, a new sample of a face that I have never seen before, right? And we'll be doing these things in the project to come. It's pretty cool. You can do that with PCA. You can do that with ICA, etc. This is a famous theorem that we have seen. Just leave it at that. If we want to do classification, however, PCA is not the approach, right? Once we are in the PCA space, if we want to do classification, then we want to use discriminant analysis instead. And here's a clear example of this. If this Gaussian distribution represents class 1 and this one represents class 2, and I find the first PC, it will be this direction, right, of maximum variance, which will give me this projection. And I'll see that the empirical error that I'm going to obtain here is much larger than this one, right? Because this empirical error has areas of all this, or actually from here to here, right? So all this will be misclassified, all this big area right here, right? Huge, terrible. We don't want that. But if I compute the LDA solution that we have derived, then the empirical error is going to be maintained. So that's what we want. This is just another way of showing the same thing. And these are some people call them the Fisherfaces, again, because of Fisher, the statistician. These are the eigenvectors that you obtain from SB or SW inverse times SB, right? The inverse of the within scatter matrix and the between scatter matrix. And now you can see that for classification, the importance of every pixel on the face is actually very different, right? Eyeglasses are no longer important, right? In fact, they're pretty much black, right? Meaning I couldn't care less about eyeglasses. That's not going to classify me people. But instead, the shape of the nose, you see this wideness here, tells you that the small changes in the width or the shape of the nose is relevant to classify people. Differences in the shape of the mouth, difference in the chin line, maybe difference within the eyes, right? Within the mouth, points of the nose, obviously a lot of eye area, eyebrows, top of the eyebrows. All these small shape differences that we have between all of us are relevant for classifying the identity of people, and that's what LDA finds. Okay, these are the basic equations that we have derived here. I'll leave you with that, and we're going to talk. I'll post a paper, famous paper of mine, long time ago, published a long time ago, called PCA versus LDA. I'll post this in Carmen, and you can see different uses of PCA and LDA in classification, but I'm just going to show you one of them here. So this is a problem, classical problem in face recognition that's called recognition of duplicates. Okay, that theoretically is a very simple problem. That's the simplest problem probably that you can define in recognition of identity. And it works like this. You have this set of images, these first two rows are sets of images of one individual, okay? Same individual. This is your training data. That's what you are given, okay? Now you're giving a test set, which are the second rows, which correspond to the same individual under the exact same image conditions as the previous one. That's why they're called duplicates, right? She's expressing the same expressions. She's producing the same facial configurations in both cases. The illumination changes that you see here and here are exactly the same. If there are occlusions, they are exactly the same. But this is taken at one point in time, and this is taken, a few weeks later. And obviously there are small differences, but we people don't have any problem recognizing this. Well, computers do, right? But with just simple LDA, it turns out that you can do very well, right? So here are the results with PCA and LDA. So PCA would be this rhomboid curve right here. And this x-axis represents how many PCs you keep, right? As you increase the number of PCs, the number of dimensions, the classification accuracy, right? This could be 1 minus or 100 minus the, or let's see, 1 minus the classification error, right? The empirical error multiplied by 100, right? To make it a probability. Then, of course, the more dimensions you include in the PCA space to represent the faces of that sole individual, then the better the classification becomes. But with LDA, which is the triangles here, you can see it goes much faster, right? And it achieves even better results. And this is in higher dimensionalities. Now with PCA allows you to go to as many dimensions as you want, up to the rank of sigma x, right? So you could go on. With LDA, you have to stop at the number of classes. In that case, there were 40 individuals, I guess. So 39 would be the maximum dimensionality you can go. But as you can see, it doesn't matter because you're almost at 90% accuracy with this dimensionality. Whereas PCA saturates, and that's pretty much it, right? There's just no improvement. It's a logarithmic function. It saturates the classification accuracy. All right. There are other limitations that I will not cover, obviously, because of lack of time. There are problems with the LDA formulations that we have presented here. So for example, if the means are the same, that is a problem, because remember, all the equations that we have is mu1 minus mu2, or mu minus mu minus mu j, right? Well, if they are the same, I have news for you, right? That's a degenerate case. So yeah, is that problem? Generally not, because the probability that the sample means are the same is pretty much 0. So, but if that distance is small, that could cause us problems. There are nonparametric versions that we'll briefly talk about when we talk about nonparametric methods. And another problem that I want to emphasize, which is in that PCA versus LDA paper, which is basically what this paper is about, said, remember, even if our underlying but unknown distributions of our classes are Gaussian and homoscedastic, like in this case, right? All I see is a small number of samples, right? So these Gaussians are defined generally in p dimensions, p potentially in the millions, and I generally have a few hundred samples at best, right? So obviously there's a lot that I don't see, right? And the problem is that in that case, you're not guaranteed to get base optimality, right? For these two underlying distributions, right, the base optimal solution would be orthogonal to this hyperplane, right? That separates them perfectly. But if these are the samples that you're given, then that is the solution that you get, right? With this classifier right here, the nearest mean classifier, which would basically divide these distributions into two, right? So the error would be astronomical. So that would be a complete disaster of applying not LDA, any classifier that we're going to talk about in conditions like this, right? And the problem is because we don't know the underlying distribution of the data, this is something to keep in mind. All right. I haven't talked about this yet. All right. I want to cover one more thing maybe before we move on. In our next lecture, I'm going to cover, can someone get the lights? My next lecture, I'm going to cover the problem of non-optimality for the first eigenvector of LDA, right? So we talk about this. And then I want to extend all these to not just Gaussians or super Gaussians or sub-Gaussians that we have seen, but mixtures of these things, okay? So we can actually define a mixture model, let's call it, that better defines the underlying, or better estimates rather, the underlying distribution of our data, okay? All right, I'll see you next time.